In this video, we are going to understand some of the concepts involved in a particular type of architecture that is very common for implementing highly computationally intensive signal processing algorithms, namely the graphics processing units or GPUs. Nowadays, you will probably hear them referred to as GPUs, in other words, general purpose GPUs. So, what are these GPUs? What is the motivation for using something of this sort? And a very brief overview of one particular example of how a GPU kind of structure could be used in order to efficiently implement a problem like matrix multiplication is what we will be covering in this. Note that this video is in no way comprehensive or even complete as far as the coverage of GPUs is concerned. It just has a very high level overview, hopefully enough to give you a flavor for what can be done using GPUs and how you could go about understanding them better. So in order to understand GPUs, we probably need to step back a little and look at the history of image processing and the kind of computations involved in image processing. Typically what we are talking about is an image is a two-dimensional grid. It would have some m rows and n columns. Each value inside this m by n grid is known as a pixel. And typically based on the fact that the human eye has a certain range of sensitivities, historically we have found that the pixels themselves were given a range of colors, usually represented using R, G, B, that is the red, green and blue, and sometimes having an additional piece of information which is sometimes referred to as the alpha channel or transparency, which is used in order to combine different images together. Overall, in other words, each of these channels or colors is given a certain number of bits, and in practice what we find is that very often we have a total of something like 32 bits per pixel, giving us a very high quality of images, to the point where using more than this many number of pixels is usually considered unnecessary for anything that is to be observed by the human eye. So in this way, images are represented as this two-dimensional grid of pixels. Now the question comes, what kind of computations or what kind of transformations are we going to apply to these images? And typically the driving factor behind this was either photographs, that is still images, which had a number of different kinds of compression techniques in order to reduce the amount of storage required. Typically these formats led to things like the JPEG format for photographs, portable network graphics or the GIF format, which were used for images that were not quite photographs but which still could be compressed significantly, and of course the relatively less compressed TIFF formats which pretty much had complete image data. Now each of these has a different level of compression, and the resulting quality of the image as perceived by human beings differs. JPEG in particular is very good from the point of view of representing photograph type of pictures with a high level of quality but very good amount of compression, much better than can be obtained using lossless compression techniques such as PNG, for example. Of course, the trade-off over there is the JPEG is lossy, meaning that some amount of information is lost in this. But when we look at the really computationally intensive portions of image processing, that comes about in the realm of video. And the kind of things that we are talking about were typically handled by a group called MPEG, the Motion Picture Experts Group. And MPEG videos are a fairly well-known standard for how images are to be represented and communicated from one place to another. Now, MPEG by itself does not specify exactly what kind of compression or what kind of encoding is to be used. There are many different codecs that can be used within the overall MPEG standard. And you will find that, because of this, there are many different ways in which videos can be represented. The important point to keep in mind over here is these are highly computationally intensive. The reason being that the sizes of the images could be anything from 640 by 480 to, let's say, high definition, which is 1920 by 1080, to even higher than that. And in addition to that, the important point is we also need to deal with the number of frames per second, which could be 30 at the low end to 60 all the way up to something like 120 nowadays. So when you have very high rates of change of images, the sheer amount of data that you need to deal with is so huge that it demands a very significantly large amount of computation. One other driving factor as far as the video or any kind of graphic processing was concerned was games. Video games were very graphically intensive and typically needed to generate large amounts of dynamic imagery or scenery. In addition, you would have objects that needed to go through transformations in real time, meaning that, let's say, you are trying to model an actual person or a human-like object that is navigating through a scene. You need to be able to visualize the scene from the viewpoint of the human being and appropriately modify it, transform it, etc. in real time. Now, what are these transformations? That is largely matrix kind of operations. In other words, what we'll find is that, let's say you have one image which has an object and you apply some kind of, let's say, a rotation transformation on it. That could be modeled as some kind of a matrix or a chain of matrix operations, which would finally result in that object being rotated by a certain amount. Similarly, we could have other matrix operations, which, for example, could take, let's say, a square or a rectangular object, process it through some kind of matrix operations, and shear it or distort it in some manner. So these kind of matrix operations can be chained together, applied one after the other, in order to apply fairly complicated transformations on objects or input images in order to dynamically construct the final image that we want to have. As a result of this, the graphics processing units that were being used in high-end video games tended to become more and more computationally capable, meaning that they were primarily focused around how to do matrix operations extremely fast. Somewhere along the line, the designers of these graphics cards realized that matrix operations need not be limited to just the transformations applied on video games. They could also be applied to other things, in particular to scientific computations. And in fact, the linear algebra kind of computations, matrix multiplications and so on, are a core staple of scientific computations. And if it turns out that there is hardware that can do matrix operations fast, there is a good chance that the same hardware could also do scientific computations extremely fast. Based on this, NVIDIA and ATI, which later became AMD, or rather was absorbed by AMD, are now known as the primary or the best known manufacturers of graphics processing units. And in fact, the NVIDIA CUDA architecture is almost considered to be the best known graphics processing unit, which also has significant applications in scientific computation these days. So what is it that makes this graphic processing unit so capable, and what are the differences from a regular processor? In order to understand that, let's take a look at what a typical CPU looks like. A CPU would typically need an ALU in order to actually do the computations, some kind of control unit or control logic that activates or deactivates the various pipeline stages, the various registers, and so on, some cache memory which can hold a reasonable amount of data for performing computations, for performing local computations, but is relatively small in size compared to the overall DRAM, which is where large amounts of storage are available and the entire data required for a large computationally intensive problem would be stored. So in typical CPUs, what you find is that this control logic is typically quite large. The reason why it is large is because you have to apply a lot of different kinds of optimizations in order to get a very high level of throughput or high degree of compute capability out of this CPU. Examples of this would be, of course, the very basic pipelining as applied in the context of a CPU. But apart from that, you would also have out of order execution, superscalar execution where more than one instruction is implemented at the same time, prediction and dynamic behavior, meaning that you are trying to predict what kind of behavior the program is going to take, predict it, and appropriately try and run the program without having any loss of clock cycles, and so on. Right? This makes the control logic fairly large and complicated and also power hungry. Now, one of the things that people noticed was while doing pipelining, you typically end up in a situation where, for example, while loading data from memory, your ALU units may not be particularly highly used. Or on the other hand, you might find that having a single ALU ends up becoming a bottleneck when you are trying to do a very computationally intensive program. So one of the things that people tried to do was to say, let's go for a many core architecture where you would have some kind of ALU plus control and sorry, let me correct that. This is a so-called multi-core architecture where you would have maybe two ALU and control blocks that share a cache memory, which then feeds off the main DRAM. Now what happens over here is we can now have two programs running in parallel. Each one has its own ALU and its own control logic and could do its own pipelining, out of order execution, and so on. They could share the cache memory, meaning that now both of these systems could share information among each other by having some part of the computation done on one processor and the remaining part done on the other processor. And the way that they communicate with each other is by means of the cache memory. Now, this works out quite well if you have highly computationally intensive problems that need to share a limited amount of memory among each other. For example, you could take this even further and then try and have something like the ALU and control blocks, another ALU and control blocks, more of them, sharing a larger cache among all of them. Or you could also have some amount of cache that is shared only among a given subset of the blocks, and the overall cache would then be shared at a different level. So for example, you would have this is shared among all the processors, whereas this smaller cache would be shared among only two of them. So in this way, we could create a sort of hierarchy in terms of the complexity of how we can share memory among different cores of the processor and manage to get some degree of parallelism out of this. Now, of course, the problem that you can see over here is the control logic is still quite large and complicated and consumes a significant amount of power. The observation that the architects of GPUs made was that for the most part, while talking about images, you could actually think of each pixel or each small block, maybe a 2x2 or a 4x4 block of pixels inside an image, as a separate unit for the computation. And if it was in some way possible to have one processor dedicated to each of those pixels or each of those small blocks, you could potentially get an extremely high level of performance out of the entire system. So how do we make use of the observation that image processing typically has a very large amount of parallelism? In other words, each pixel could potentially be processed independent or at least simultaneously with a lot of other pixels. So the architecture also should sort of reflect that kind of a structure. In other words, the architecture that the GPU architects came up with was something which looked similar to the pixel array that exists on an image. So rather than having large ALUs, large control units with some amount of shared cache and an interface to DRAM, the structure that was adopted was something more like this. Have the DRAM interfacing to large blocks of small amounts of memory, relatively small caches, so to say, and a very large number of processors. So in other words, you would have a very large grid of processors that would then exist across the system. And each block or each rectangle that I have over here would essentially be one processing core. This architecture is what is nowadays commonly referred to as the many core architecture, as opposed to the multi-core architecture which you typically see in CPUs. The primary difference over here is how are we able to get such a large number of small cores? By stripping away a lot of the control, simplifying the logic, eliminating a lot of the out of order and speculative execution, and saying that each individual core over here is such a simple, is a relatively simple piece of hardware, of course still capable of computing and in fact performing floating point computations, but it just does one job, which is the floating point computation, and does it well. In that way, what we can do is create a large number of cores of relatively small size and fit them onto a single silicon die, have large amounts of distributed cache, so to say, which is split up in such a way that either single cores or blocks of a few of these cores together share a certain amount of cache memory and are able to make use of that and share information among themselves. In this way, the architecture changes significantly. The way that you use the silicon has changed dramatically. Whereas previously we had a situation where for a given area of silicon, what you would do is divide it into maybe 4 or 6 processor cores and a certain amount of cache memory. So this would basically be CPU 0, CPU 1, CPU 2 and CPU 3, which means that each CPU is large, complex, high performance in the sense that it has a lot of speculative execution and various other tricks that allow it to perform at very high speeds. The revised model basically says we will have a cache that is distributed among a large number of processors. And by large, we literally mean extremely large. The numbers are in the thousands, not even in the tens. So each one of these becomes a CPU, or to be more precise, it is called a core. In terms of NVIDIA's technology, this would essentially be called a streaming processor. And the reason it's called a streaming processor is because, as we have seen, signal processing applications generally can be viewed as streaming in the sense that there is a stream of data coming in, being processed and pushed out. These processors are specialized and highly tuned to perform well on such kinds of workloads, where the data essentially needs to move into the core, be processed in some way, and then either handed over to an adjacent core or back to the main memory. In that way, the cores that are designed over here are not generic. They in fact are not really capable of running operating system level code, but would be very effective at running the kind of computations required for either an image processing or a scientific computing application. Now, with all of that background, let's try and understand how a problem like matrix multiplication could be implemented effectively on an architecture such as we might find in a GPU. Note that this is not a detailed explanation over here. In fact, although I will be showing snippets of the for loops that are involved in the multiplication, I will not really be providing CUDA code or anything that is at a level that can be actually implemented on a GPU. The focus is on just analyzing and understanding the implementation at the level of the for loops themselves. That in turn means that the same kind of analysis that I describe over here also applies when you are trying to implement matrix multiplication effectively on a different kind of architecture, in particular, let's say on an FPGA. So many of the concepts that we will discuss over here will also apply if you are trying to do a parallel multiplication of matrices on an FPGA type architecture. So what exactly does matrix multiplication involve? We want to multiply two matrices. One is A, which is of size m cross k, and multiply it by a matrix B, which is of size k cross n. Notice that the k has to of course be common. This is well known, because otherwise you cannot do the matrix multiplication over here. And of course the result of this is going to be another matrix C, which will have size m cross n. So C m cross n is equal to A m cross k multiplied by B k cross n. A very simple way of writing a code for this, essentially, let's first visualize what this looks like. Essentially what we have is a matrix A of size m rows and k columns to be multiplied by a matrix B that has k rows and n columns, giving us a result C that has m rows and n columns, right? So this is ultimately what we are going to do. Now, what exactly is the computation itself that's involved over there? I will use the term Cij to refer to the ith row and the jth column of C, which means that I can essentially write my matrix multiplication using this series of three nested for loops. For I is equal to 0, I less than m, I plus plus. I'm assuming that I have a language which is C or something very much like C. For j is equal to 0, j less than n, j plus plus. For k is equal to 0, k less than k, capital K, k plus plus, and the operation itself is Cij equals Cij plus A I k into B k j. Notice that I also need to initialize Cij to 0. I could either do that here or outside the loop over here. I'm leaving that out because part of what I'm going to be doing is demonstrating how the loops can be modified in their order or in their structure. So I don't want to worry about how the initialization is done. We will assume that the initialization of Cij to all zeros has either been done initially itself before the loop starts, or after the inj loops before we start the k loop in this case. That will of course cause a little bit of a problem later when we change the order of the loops, which is why I am leaving that part out of the discussion for now. Alright, so in other words, the C code that can implement a matrix multiplication like this is very straightforward, almost trivial. The question is, what would make this either fast or slow, and what would affect the performance of the total computation? For that, one of the things that we would like to understand over here is, what is the total number of computations involved? And to keep things simple, I'm going to assume that m is equal to k is equal to n, and all are just represented by the value n. In other words, I am multiplying two square matrices n cross n and getting a result which is also n cross n, right? Note that none of the analysis that I have over here changes significantly based on this. Some of the details in terms of what can fit into what kind of memory does of course change, and in practice it's not always meaningful to just approximate matrices as square matrices. But for the present discussion, it does not really change our arguments too much. So if I make this simplifying assumption, effectively the total number of computations is approximately order of n cubed. Why is that? Basically, I have 3 nested for loops, each running from 0 to n minus 1. Right? So I have n into n into n iterations of the compute step, right? The compute step being this one here, right? I could alternatively also write this as n cubed multiplications or n cubed MAC, multiply accumulate operations, because after all that's what I'm doing. I'm multiplying two numbers and adding it to something else. It doesn't matter. The point is the n cubed is what we are primarily concerned with on a big O, that is the order level of estimation. Now, what is the total amount of data involved? A is of size n cross n, so is B, and so is the result C. So what we have is basically n squared plus n squared plus n squared data points, right, or values, which basically means order of n square total data. So another way of looking at this is I need to do order of n cubed computations over order of n square data. The data itself needs to be loaded from memory into the compute unit or the processor, used in some way for doing some kind of computation, and then will be discarded. So ideally, I would like to have a compute intensity, or the number of computations performed per data loaded, which is going to be O of n cubed by O of n squared, or in other words is going to be O of n. What does this mean? Effectively what I'm trying to say over here is for each value that I load from memory, I would like to perform n computations, perhaps n multiplications, before that value is discarded or left unused, right? Or another way of putting it is, in the ideal situation, I should only load each value of either A or B from memory into the processor one time, make use of it as many times as I need, in other words, n order of n times, and then never load it again from memory, right? Why is this a concern? Because the main bottleneck as far as implementing a matrix multiplication of this sort is the fact that matrices occupy a significant amount of memory, and loading and storing data, in other words loading data from an external memory, which is typically going to be DRAM, is slow and expensive in terms of energy consumption as well. So overall, if I can reduce the number of times I have to access memory, or each time that I access memory I should be able to use that data a large number of times internally before I discard it, that is the ideal situation that I'm looking for. So let's also get a clearer understanding of the memory hierarchy that we are talking about over here. We basically have a concept of some kind of a CPU or a processing core, it doesn't matter what, which talks directly to a cache memory, which in turn talks to a large dynamic RAM, DRAM, right? Now the CPU has only registers for internal storage. This will be on the order of tens, meaning that a typical RISC processor these days would probably have 32 registers. Other processors might have fewer. In some cases, they might have a little bit more, maybe 64 or at most 128 registers, but almost certainly not more than that. That's literally just the capability to store tens to at most hundreds of values. A cache memory is something which has high speed access, high speed and low latency access, meaning that if I need to access something from cache, once I give out the read address, I will get back the data within a matter of nanoseconds, within 1 or 2 clock cycles, as opposed to the DRAM where it can typically take much longer. This low latency access of course works only for a limited amount of data. Typically we have tens of kilobytes of the so-called L1 cache, which is the first level cache closest to the processor. You then have L2 cache, which could at most go to maybe several hundreds of kilobytes, possibly in the low megabytes, but that's also very unlikely. And then you might have an L3 cache, which in turn could go up to maybe a few megabytes, but is going to be slower than the L1 and L2 caches. DRAM, on the other hand, is very high capacity, but correspondingly also has a very high latency of reading. It might have a high throughput, which means that once you are able to read data, you can actually get data in a large burst and very fast. But the problem is the very first access, the first value that you want to read from DRAM could potentially take even hundreds of clock cycles to arrive. This is megabytes to gigabytes. So the capacity, in other words, for DRAM is extremely large compared to what you can do with cache memory. Now, what kind of memory are we talking about for matrix multiplication? Supposing n is equal to 100, what we are basically saying is A, B, C together totally will take 3 into 100 squared, or approximately 30,000 memory locations, which, assuming that we are dealing with single precision floating point numbers, is approximately 120 kilobytes. This is not much. This is quite small and in fact could potentially even fit within the cache memory of a reasonable processor these days. But what if n is equal to 10,000? Now what we are talking about is the total capacity is 3 into 10 to the power of 8 memory locations, which is approximately 10 to the 9 bytes or 1 gigabyte. No processor that we know of today has cache memory even in the hundreds of megabytes range. So forget about 1 gigabyte. It is almost certainly impossible to store store matrices of this size directly in the cache memory of your system. What that means is accessing the DRAM has to be done in a very planned and careful manner, so that you are able to basically go in bursts and read large chunks of data in bursts from the DRAM, store it into the local cache, make use of it, and then finally discard it when not necessary. So let's go back and look at the source code that we have, which is basically the for loops. For I is equal to, I'll just rewrite this in a slightly simpler manner, 1 to n. For j is equal to 1 to n. For k is equal to 1 to n. Right? C of ij equals or plus equals a of ik into b of kj. What does this mean graphically? Let's try and visualize what exactly we are doing over here. Right? The resulting matrix C needs data to be read from A and B. Of course, we have chosen the option of them all being n cross n just to keep things simple. So what does that mean? Effectively, what we are saying is the k index is going along a row of A and a corresponding column of B, and these values accumulate to give us the C of I j. This value is the ith row of A, which basically corresponds to the values A of I comma k equal to 1 to n. And similarly, this is the jth column of B, which is B of k comma j, k equal to 1 to n. In other words, the access pattern that we are talking about is going to be something like this. I will first access C of I comma j equal to 0, store it in a register. Then for I equal to 1, read all B of k comma 1 values, multiply and update C. Then read all B of k comma 2 and update C. Repeat like this until I read all B of k comma n and update C. You will notice that in order to have done this, I would basically have read in the entire row A of I comma k. This row is read once, but column B of k comma j is read for each of these values, read once for each value of ik. So in other words, overall, what I am going to do when I run through the entire computation, it is going to involve read one row of A, store it into a cache from where I can access each element of the row quickly. But for this, I would then need to read each and every column of B. Now, if I need to read each and every column of B, and I have already assumed that the overall size of B is so large that I cannot store the entire thing into a cache memory, effectively what it means is that as and when I read the columns of B, I would need to throw out previously read columns. And then when I reach the next row of A, I would need to read in those columns of B one more time. Effectively what it means is B needs to be read from memory a total of n times, once per row of A. So in other words, the reuse factor for A is not bad. A, I read a row once, compute many values, then don't read again. But B, read each column n times, which implies that the entire matrix B has to be read n times. So effectively, in other words, the data transfer that I require for this mode of implementing matrix multiplication means that even though I might be able to get away with reading A just once overall, the matrix B will have to be read a large number of times. And effectively, I will not be able to get a compute intensity anywhere close to n. I will probably end up with a compute intensity closer to 1, meaning that for each value that is read from memory, I pretty much do one computation before I throw that value away and have to read it again at a later point in time. So the question that will arise is there a better way of rewriting this code in such a way that I can read the values of A and B just once each and perform as many computations as I can with it and then update it? One way of doing this is by recognizing the fact that the matrix multiplication that we have written over here uses the so-called inner product. What does the inner product do? It basically says A of I comma k is multiplied by B of k comma j. This is a row, this is a column, and I take the dot product or inner product, gives me one scalar result of C. Another way of doing matrix multiplication is to try and do something called an outer product. Over here what we will do is, let us, rather than taking the ith row of A, let's take the kth column. In other words, the kth column of A corresponds to the values ik for all I rather than for all k. And similarly, the kth row of B corresponds to the values B of k comma j for all j rather than for all k. Now, if I take these values, right, in other words, the kth column of A and the corresponding kth row of B, what I get when I multiply these two together is one value which I'll call Ck, which is a partial outer product of the kth column of A with the kth row of B. In this way, I can create several different partial products, C1, C2, C3 and so on, each corresponding to a different value of k. And now by adding all of these together, I will get the result C will be the summation of these Ck matrices, which are in turn outer product matrices. Now the question is, how does this help us, right? So we are basically interested in understanding whether this approach using the outer product can give us better performance than the original inner product based method. Now, how is it possible for this to give us a better result? Let's look at the data usage, right? The data access patterns for the outer product based method. I need to access the kth column of A and the kth row of B, use them, create an outer product, generate the value Ck, store this somewhere once, and never read the kth column of A or the kth row of B again. So in other words, it looks like as far as A and B are concerned, I might have actually achieved what I wanted. I read each of the values in A and B exactly once, compute an outer product, store it somewhere, and thereby access a total of O of n square elements, perform n cubed computations with it, and I have completed the matrix multiplication without requiring me to access the values of A more than once or B more than once. So it looks as though this outer product based method might have actually solved the problem, except of course for the obvious catch. What about C? The values of C themselves need to be stored somewhere. In fact, I need to store all of these outer product matrices, or I need to be able to read in the temporary partial values of C and add them up on the fly. Either way, I will need to access C quite a lot, right? So the question becomes, have I just transferred the problem of access from having to read B many times to to requiring my computation to read the values of C many times instead? Okay. And to some extent, that is in fact the case if we do this in a naive manner. One possibility is, if C could fit in on-chip or cache memory, then this outer product method works. What does that mean? It means that the entire C matrix could be stored somewhere in on-chip memory. The values of A and values of B need to be read in, but will be read in only once. An example of this could be a situation where, let's say that I had A m cross n multiplying, or m cross k multiplying B k cross n, and let's say that m is equal to 100, n is equal to 100, but k is equal to 10,000. In such a situation, if I needed to read the value of B k cross n a large number of times, as was the case in the inner product algorithm, then I would end up paying fairly high penalty for memory access. But C, on the other hand, is going to be a 100 cross 100 matrix, and this could potentially even fit in on-chip cache memory, which means that I can then use the outer product based method in order to very efficiently complete the computation. Of course, this is a special case and in fact doesn't solve our problem at all for the square matrix situation. So what can we do instead? Now, both in the context of general parallel processing systems or in the case of specialized architectures such as GPUs, the basic idea that we use in such a situation is something called tiling. What we say is, I want to compute C. Can I break this computation up into smaller segments? In other words, can I perhaps find one part of C that needs to be computed, find out all the computations that are required for that part of C alone, do them, and then discard everything else? So let's see what is required to compute the values of C in the shaded area shown over here. What we effectively have is that we will need to use the two matrices A and B, but the areas of A and B that we need to access essentially correspond to this row and this column. In other words, it's the overlap of this set of rows of A with this set of columns of B that finally results in computing this set of values for C. Now this looks once again as though we are trying to do some kind of an inner product, but the approach that we are going to use instead is to say that rather than just straight away doing an inner product, we will break A and B into matrices which have these narrow strips and then use the outer product algorithm on each of those computations. How does this help us? As we have already seen, as long as this is kept small enough to fit in the on-chip cache, the outer product method will be effective, right? Meaning that I will need to access A and B, the areas corresponding to this shaded area of C. I will need to access the corresponding data from A and B in an optimal manner. Just read them once in order to compute that portion, right? Of course, the problem is I will need to store all of this portion of C somewhere in a way where I can access it efficiently, but that is precisely what I mean by saying that is small enough to fit in the cache. Once this part of C has been completely computed, it can be discarded, or rather stored back into the main memory, and never needs to be touched again. On the other hand, what I will find is that when I do move on to, let's say, the next segment over here, I will need to read the values, a fresh set of values of B, but I will need to read this set of values of A once again. In other words, the reuse factor for A is no longer n. It's not that I can just read the value once, compute n values, output values with it and be done with it. I might actually have to read the values from A multiple times, one for each set of columns of B. However, by appropriately choosing the values of the width that I choose over here, and similarly the width that I use over here, I can create a intelligent mapping of segments of the output matrix to regions of the cache memory and thereby regions of the processing space in such a way that I can perform each of these computations in a simple manner by storing the output data directly in the cache memory. And of course, this W can be chosen in such a way that n by W could be as small as possible. In other words, I choose W as large as possible. Right? What do I mean by as large as possible? W should be as large as possible that would still fit within the cache memory of the system. But subject to that, I could basically break up the number of times that I need to reread to a factor n by W rather than n. How does a system like a GPU make use of something of this sort? The architecture of a GPU is precisely suited to something like this. Basically, what we have over there is we have a large number of processing cores and we have shared cache memory or cache blocks. What this effectively means is that some number of cores over here will match up with some number or some amount of cache memory over here. And similarly, we would have another set of cores matching up with another amount of cache, cores and cache and so on, right? And by doing this, by having these blocks over here, we can essentially assign each of these blocks of processing elements along with the associated cache to compute a part of the output matrix. You will notice that this is in general a parallel algorithm. All that it's saying is how do I break up a large matrix computation into smaller parts in such a way that the communication or the rereading of data that is required across different parts of the computation is kept as small as possible. And that is exactly what we are doing. So in general, you will find that most GPU computing algorithms are also based on core ideas of parallel processing. The main difference that comes about in the case of GPUs is the sheer number of cores can be so large that you really need to think in terms of how you can parallelize across such a large number of cores, rather than worrying about how you can have a fairly complex algorithm that runs on each individual core. You need to go the opposite way and try to find out simple algorithms that can run on the individual cores and how they can work together in order to get an overall efficient computation of the overall final result. GPUs therefore are one specialized kind of architecture that is usable for many kinds of highly compute intensive signal processing applications, primarily of course being in the image processing area, but also applicable to a number of other signal processing applications itself. The core idea of course over here is that you are using a large number of processing cores. Each core itself is very simple. The cores are grouped into blocks that share a certain amount of memory that allows them to then partition the complex programs into small portions that can then be handled by these blocks of processors.